Alright, I hope you got a lot of time on your hands because this is the big one. This is the money chapter. Chapter 7, EIGRP, Enhanced Interior Gateway Protocol. This video is probably going to be a little bit long, so make sure you can schedule yourself some time or watch it in 2 different parts. Alright, so we're going to talk about EIGRP, how to configure it for IP4, how it works, and then how to configure it for IP6, and then talk about wrapping it up. So, there's your objectives, blah, 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 blah. Remember, just hit pause if you want to read those. So, EIGRP. As far as routing protocols go, 1992 is a pretty recent protocol. Most of our stuff has been developed for, the 80s and 70s. And then, remember, EIGRP is a Cisco proprietary protocol, which means in order to run EIGRP, you have to have all Cisco routers. But in 2013, Cisco released the basic functionality of EIGRP as an open standard. Now, what does that mean to you? It means other companies out there can implement EIGRP into their equipment, and then it would be able to function with Cisco stuff. So you may see other routers now out there that are able to perform EIGRP along with Cisco routers. So that's probably helped Cisco a lot. Remember, Cisco invented routers. They didn't invent switching. They actually bought a company that had invented the switching stuff. So in the early years, they kind of got, I don't want to say got ripped off, but really they did. Like Cisco invented VLANing. And they had what they called the ISL protocol, and then the rest of the world said, "Oh, hey, that's really cool. We can't steal it from Cisco, but we'll make an open standard based on that." And then it's .1q. And it's the same way with EIGRP. They released IGRP, and then the rest of the world's like, "Hey, we need something that competes with that, so we'll make open shortest packet first." And then Cisco had to make EIGRP. So Cisco has made a lot of firsts out there, and then somebody else makes a different thing, then everybody kind of adopts the different one because it's open standard. So Cisco releasing EIGRP as an open standard has kind of really helped, and I hope they do more of that. So it's an advanced distance vector routing protocol, and now, again, it depends on which book you read. Remember, there's distance vector and there's link state routing protocols. OSPF is a link state. It monitors the links, where a distance vector looks at the distance and direction to the target. Some books will tell you it's a hybrid. Some books will tell you it's an advanced distance vector routing protocol. I've never seen it listed as a link state protocol, but so don't worry about that too much. Okay. EIGRP uses an algorithm called DUAL, the Diffusing Update Algorithm, to calculate paths and backup paths. And it does this, and it produces some pretty big numbers. There's typically 8 to 12 digit numbers as their metric. So when you see those big numbers, you know right away in the metric, oh, I'm probably dealing with EIGRP. Alright, they obviously, just like OSPF, it establishes neighbor adjacencies. Hey, I'm speaking EIGRP. Hey, so am I. Hey, let's be buddies and be neighbors. Now, when they developed EIGRP, no existing protocol at the time worked for them, because sometimes they needed to send connectionless packets, and other times they needed to send connection-oriented packets. So they couldn't use TCP or UDP. They really wanted to use both. So they kind of came up with their own protocol called Reliable Transport Protocol. And I've also seen this labeled as Real-Time Transport Protocol. But it's RTP. So RTP is a protocol that's built into EIGRP to deliver packets to neighbors. And it has a bunch of extra features in there. So that's the only place I've ever seen it used, is in EIGRP. And again, it's only because TCP and UDP at the time didn't do what they wanted to do both together. Alright. It sends partial and bounded updates, which means it only sends a partial update. So if something changes, it only sends the update about the change. And by bounded, it only sends the update to those people that need the update, not to everybody. So think back to RIP, that sends a complete routing table to all of its neighbors every 30 seconds, whether they need it or not. So it sends a lot less traffic on the network as far as their updates go. And it supports equal cost load balancing and unequal cost load balancing, and that's really the big factor with EIGRP. As far as I know, it's still the only routing protocol that does that. So if I got dial-up to one in one direction and I got a T1 in another direction, it will load balance between the two. Now what it'll do is it might send one packet down the dial-up and 10 packets down the T1 because it's 10 times faster or something like that. But it'll do unequal cost load balancing and calculate the difference between the two speeds, and so that the packets get there in the optimal time. So it's pretty cool in that regard. All right, with EIGRP you have three tables. You have the routing table, the neighbor table that kind of everybody else has. So remember, your routing table is all your routes. Your neighbor tables is who's directly connected to me. And then you have a topology table. In the topology table, they have primary routes and then backup routes, if they have a backup route to that destination. Now, their primary routes are called successors, and their backup routes are called feasible successors. Now, if these slides get into that, I'm just going to kind of glance over that stuff, and I'll link you to another video that I do for that's about 20 minutes describing how this successor, feasible successor kind of thing works out for you. So you might have another video to watch in addition to this other long video that we're watching for now. So sorry about that, but again, this is the bread and butter topic. This is, you know, Cisco's bread and butter, the EIGRP. This is the one you're going to have to know. There are a lot of diehard Cisco shops out there. You know, like when I was coming up, the local hospital was all Cisco, and their guy was, you know, Mr. Cisco, and he wore Cisco shirts every day, and he didn't even want to talk about having non-Cisco stuff in his hospital. So again, EIGRP. All right, enough said. So remember, they have their own transport protocol that they had to build. And RTP is flexible. It works with IP4 and IP6. It does connection-oriented stuff. It does connection-list-oriented stuff. So it replaces the TCP part. Because again, sometimes it did not need a connection. So don't forget, RTP is the protocol that Cisco developed as their transport protocol to work with EIGRP. All right. EIGRP supports authentication, so we can build keychains and have our routers authenticate to each other. So we're not sending updates to routers that we don't want to, things like that. And again, in your very secure networks, you know, banks, anything financial, healthcare, we typically see authentication being used. All right. Make sure you know these 5 packet types. So EIGRP uses 5 packet types, just like OSPF, but they name them a little bit differently. So the hello packet. The hello packet is used to discover other neighbors in the area. It's like, hey, hello, anybody out there? And then an acknowledgement is used to acknowledge the receipt of any EIGRP packet. Now remember, with OSPF, you had specific packets that reply to specific packets. So if I sent you a link state request, you would send me a link state update. But in EIGRP, everything gets acknowledged with an acknowledgement. So an update sends routing information. A query is used to ask a neighbor for extra information. Then a response, a reply, is a response to the query. So what would happen is, hey, let's say you send out an update. Hey, I know about network 10.0.0.0. Well, then my router's like, oh crap, I don't know about that. That's not in my table. So I'll send you an acknowledgement on your update, and then I'll send you a query. Hey, can you give me information on 10.0.0.0? And then you'll send me an acknowledgement to the query, and then you'll send me a reply with that information. And then I'll send you an acknowledgement to the reply. So that's where the acknowledgement stuff works in there. So make sure you understand how those packets operate. All right, so the hello packets used to discover EIGRP neighbors and to form those adjacencies. Hey, here's my information and here's me. Can we be buddies? Oh, sure, my stuff matches. Let's be buddies. All right, and it's sent in IP4 and IP6 as multicast. So in IP4, we multicast it on 224.0.0.10. So remember, OSPF is 224.0.0.5 and 224.0.0.6, but EIGRP is 224.0.0.10. All right, in IP6, we multicast that on FF02:A. And that's the unreliable delivery stuff. You know, when we're pushing out the updates or the neighbors, we don't expect a reply. You know, what if my neighbor is a switch, or my neighbor is you know, a PC or something like that? I don't expect a reply. So in that case, TCP wouldn't work, because TCP, you know, requires acknowledgments and sequence numbers, and it's reliable. So that's where like the UDP version would be needed. So that's why they had to develop that RTP, because it does both. All right. By default, hello packets are sent every 5 seconds. Now, on non-broadcast multi-access networks such as Frame Relay, they're every 60 seconds. All right, and then EIGRP uses a default hold time of 3 times the hello interval. Now, what that hold time says is, I won't consider you down until the hold timer is reached. So after 3 times the hello time, so after 15 seconds, if I haven't heard anything from you, I will assume you're down. So that's the hold time. I hold off on declaring you down when the first hello packet doesn't get there. And that way, you know, in case a hello packet gets lost, or for some reason somebody disconnects a cable and plugs it back in, or something like that, it doesn't take that network down. You know, so the hold timer is there for 3 times, so 15 seconds, which is that's a pretty nominal time. But again, you can change that stuff if you want to. All right. So remember, with EIGRP, update packets are sent to propagate routing information only when necessary. So if there's no update needed, everything's all configured, there are no update packets sent. They're just, you know, the typical small hello packet saying, hey, I'm still here, I'm still alive. Are you still there? So you can see, compared to RIP, obviously there's a lot more benefit to running OSPF and EIGRP than running RIP, because again, partial updates only sent to people that need it, that kind of stuff. All right, updates use reliable delivery, therefore they require an acknowledgement. So anytime I send an update, I expect an acknowledgement. When I send a hello packet, I do not expect an acknowledgement. All right, so if for some reason there's information in the query or the update that I send out, and then you're like, oh, hey, I don't have that information, can you give me more? Then I send a query, which can be multicast or unicast depending on the situation. And then I'll send a reply to you with that information. Hey, I need to know more information on the 10 network. Oh, hey, here's the reply, and here's the information on the 10 network. All right, so here's kind of the header kind of stuff. So at layer 2, you know, we've got MAC addresses. At layer 3, we got the IP address. And then we have an EIGRP header that has like the autonomous system number. And then we have an LTV type header where what kind of route this is from EIGRP. Is it an internal route? Is it an external route? And then the parameters. What's my hello time? What's my hold time set to? Things like that. So all that information is kind of put into the EIGRP header. And then there's the little part where the EIGRP header is. Now remember, when we look at these things, it looks like, oh, hey, these things take up so much more space, and there's only like a small box for the data, so it looks like the headers are actually bigger than the data. But that's not true. You remember, our maximum transmit unit size is 1500. So that's typically what we said. So 1500 bytes. But these things are only 31 bits. So the entire header is enclosed in 31 bits. All right, how to configure EIGRP for IP4. So again, the course uses the standard 3 router, but then there's going to be an ISP out there, and we use that probably to simulate the default route that we're going to put in there. All right, so in order to turn EIGRP on, it's just router EIGRP and then the autonomous system number. Remember, now this number is important in EIGRP. In EIGRP, in order for us to form a neighbor relationship, our autonomous system numbers have to be the same. So while in OSPF they call that the process ID, sometimes in some books, depending on where you read, it'll call this the process ID / autonomous system number. So remember, in OSPF, that number does not matter, but in EIGRP it does. That number has to be the same, because so in OSPF we create areas with our network statements, but with EIGRP we create our autonomous system numbers, and that's what separates us. And that way my router can be in autonomous system 10 and only send updates to other routers in autonomous system number 10. Your router may be in autonomous system number 5 and only send updates to your stuff. And that's how we separate networks. So we don't separate them with areas, we separate them with autonomous system numbers. So router EIGRP 10 will only send updates to other routers in EIGRP 10. Alright, then all the other stuff is about the autonomous system number. It's only significant to that routing domain. The internet providers that use BGP actually get autonomous system numbers from the Internet Association that controls the entire internet. So they have to be assigned. So our stuff is only significant to our different networks. So don't let that stuff confuse you. So again, router EIGRP1, boom, and that's it. So just like OSPF, you're going to have a router ID, but in OSPF, that router ID determines who's going to be the designated router. EIGRP does not use a designated router, so it doesn't really care about the router ID. The router ID is not very significant in EIGRP. In EIGRP, every router learns all the information from the other routers and then builds his own table. So it's kind of like every man for himself. So it's possible for your routing tables to be different on different routers. So jumping back to this slide, we also then make network statements like we did in OSPF, and hopefully those will show up here in just a minute. So if you wanted to configure the router ID, you can do router EIGRP 10 or router EIGRP 1, enter. And then from the EIGRP prompt, so it says config router, you would type EIGRP space router ID space the IP4 address that you want to put in, 1.1.1.1, 2.2.2.2.2, blah, blah, stuff like that. The IP4 loopback address can also be used as the router ID. So if the EIGRP router ID is not configured, the highest loopback is used. And loopbacks are nice because they don't go down, because they're virtual. They're not connected to anything, so you don't have to worry about the other end unplugging and taking your interface down. So interface loopback 5, enter, and then IP space address space 1.1.1.1, enter space the subnet mask. So however you want to do it. Now don't forget, the router ID is not as important in EIGRP as it is in OSPF. Alright, now we get into the real stuff, the network commands. So remember, the network commands advertise only directly connected networks to the router. You would never want to advertise a network that's connected to router 2 on router 4. Why would router 4 be advertising some remote network? He doesn't know about that remote network. He's not directly connected. So only do network statements for your directly connected networks. Every class when we do this, there's always somebody that starts advertising all networks from all routers, and it's like, what are you smoking? If every router advertises his directly connected networks, then every router would talk to each other, and then every router would know about every network out there, and that's kind of how it works. I only talk about what's in my pockets, and you talk about what's in your pockets, and then Joe Bob talks about what's in his pockets. Then we all share that information. Then we know what's in all 6 of our pockets. That kind of makes sense? So that way, there's no room for error. Nobody's doing hearsay. Oh, I heard it from Joe Bob that he's got something in his pocket. It eliminates all that stuff. So we only advertise directly connected networks on a router. Now, these network statements don't have to match exactly. So in other words, let's say I got 3 interfaces on my router. One interface goes to 192.168.1, one interface goes to 192.168.2, and one interface goes to 192.168.3. I can advertise network 192.168.0.0, and that matches all 3. So I can use one network statement to match all 3 of my networks. So like here in this case, on the router 1 that they're showing, he actually has 2 172.168.1 and 172.168.3 interfaces, but he's going to advertise 172.168.16. Now, when you say I advertise network 172.168.16, the router then looks at his interfaces, and whatever networks are on those interfaces that match, those are the network he advertises. So in this case, this router would say, hey, 172.168.16 matches this interface and this interface, so I'm going to advertise 172.168.1 and 172.168.3. So the network statement just tells the router which interfaces to advertise. So it doesn't tell you what networks you're going to push out to everybody. It tells you what interfaces on the router you're going to advertise, if that helps. So it's kind of a weird, complicated process. It's best to not abbreviate this stuff and to be as specific as possible and just advertise 172.16.1 and 172.16.3. And the reason for that is, what if later on I add an OSPF network or something like that, and I create it as 172.16.2? Well, then the network statement EIGRP is going to start advertising that out, and I may not want to advertise that out. So as far as our class goes, you normally want to be as specific as possible in the real world. But on the quizzes and the labs and the exams, you can just use general statements like this to advertise everything that's captured. Now, if this is confusing for you at all, ask the question in class. Hey, could you talk about that network thing again and those network statements and how they work? And I'll draw it on the board and tell you and talk, and in 5 minutes it'll all be clear to you. So again, you're paying for the class. Might as well ask those questions. All right, move. All right, so EIGRP log neighbor changes command is on by default, and that will display any change in neighbor adjacency. If one neighbor shuts down or his internet comes unplugged or his cable comes unplugged, you'll get a system message. It'll log that change, and it'll verify those neighbor adjacencies during configuration. So that'll tell you right away whether you've had anything or any neighbors have come and gone. All right, and then the network command. Why they jump back and forth this, I have no idea. It drives me nuts. So on the network command, when you're advertising networks, they would like you to use the wildcard subnet mask, also sometimes called the inverse subnet mask. Now, the newer iOSs allow you to use the regular subnet mask without inverting it, and it'll invert itself, or it'll handle that for you. But on the CCNA, for some reason, they always assume that you're using the oldest possible iOS out there, and you'll have to do the invert subnet, or the inverse. The inverse subnet mask. So you'll have to do the wildcard subnet mask. So make sure you understand how to do this. Basically, you just subtract the regular subnet mask from all 255s, and that gives you the inverse subnet mask. All right, other router commands. Passive interface. Remember, I don't want to push EIGRP updates out the same interface where there's just PCs and switches. A PC or a switch has no need for an EIGRP broadcast. It doesn't need to see those hello packets every 5 seconds. That causes unnecessary traffic. Remember, our job is not to keep the network up. That's an easy job. A monkey could keep the network up. Our job is to make the networks run more efficient. And by removing hello packets from our interior networks or our LANs, that helps. So we use passive interfaces to stop sending updates out a particular interface. So again, I go router EIGRP1, enter, and then passive interface FA00. Now, a lot of times in your book, they recommend you do router EIGRP1, and then passive interface default, which makes all the interfaces default, and then you go and you turn on the ones you want to use. So no passive interface 0000, no passive interface 001. That kind of stuff. So you may see that written as well. So I think that's the best practice method. I could be wrong though, and I frequently am. So do passive interface default. That way any interface that gets added is automatically not advertising your stuff. And then you can only allow the updates or the interfaces that you want. But in our class, you're okay with just doing the passive interface on the local network. So just make sure that you understand how both ways work. It's always easier, as far as security goes, to block everything and to allow the allowed traffic than it is to try to block all the bad stuff. You could spend forever trying to block all the bad stuff, but it's a lot easier to allow the good stuff, if that makes sense. So passive interface default, kill everything, and then I'm only going to allow what's needed. So again, depends on where you go. All right, and then the big command, the show IP protocols command, that's your bread and butter, will show you that I'm running EIGRP, what my autonomous system number is, what my router ID is, although those doesn't really matter in EIGRP, and I'm talking really fast, blah, blah, blah. What networks you're advertising, things like that. And if I come over and I do a show IP protocols on your lab, and because you called me over because stuff doesn't work, and I see 14 network statements and you only have 3 that are needed, I'm going to cry. All right, so show IP EIGRP neighbors will show you your neighbors. and some other information about them. Their IP addresses, so that's your neighbor's IP address. How many seconds until I call them dead? So in this case, hey, 11 more seconds. If I don't receive a hello timer, I'm going to call this router dead. At 13 more seconds, I'm going to call this one dead. And then how long I've known about those routers or those neighbors. So a lot of interesting information to show IP EIGRP neighbors. You can also do show IP EIGRP neighbors detail, or was that show CDP neighbors detail, and find out more stuff about that. So don't forget, there's show IP EIGRP neighbors shows you information on your EIGRP neighbors, and show CDP neighbors shows you information on any Cisco neighbors. So EIGRP neighbors isn't going to show you information on a switch, but show CDP neighbors will. Alright, and then the bread and butter command, the show IP protocols. Hey, I'm running EIGRP autonomous system number 1, so everybody has to be in system 1. My router ID, my administrative distances, auto summarization is disabled, what networks I'm advertising, and then other information. So most of the time, show IP protocols will solve your issue. The information will be in that command to tell you what you did wrong. And 9 times out of 10, you're advertising the wrong networks or your autonomous system number is not correct. Alright, and then if you do show IP route, you'll get your routing table. And then obviously with EIGRP, the routes show up as D, which is used for the dual algorithm, because E was already taken by something else. So don't forget how to read the routing table. This is the remote network that I know about. This is my administrative distance of EIGRP, which is 90, and this is my metric. Remember, I told you it calculates a big long number. So anytime you see these long numbers, you're talking about EIGRP. So I get to that network by sending to this network. That's my neighbor that I send to. I've known about the network this long, and I send it out my serial 000 interface. Remember, anytime you see a via an IP address, that's always your neighbor's target. That's the next step in the chain, the next hop in the travel, or whatever you want to say. That's always your neighbor that you're sending to. And when you see a name 0000, that's always your exit interface. Your router knows itself by name, but he knows your neighbors by their IP addresses. Alright, so EIGRP operation. Alright, so the neighbor adjacency. So I turn router 1 and router 2 on. And they're both configured with EIGRP. So a hello packet goes from R1 to R2. Hey, I'm router 2. Anyone out there? And then he actually, so router 2 gets it and says, hey, there's another EIGRP router on my network. I'm going to give him my information. So, hey, here's an update. Here's my routing information. And then I send him my hello packet. Hello, I'm router 2. Is anyone out there? So when a router receives a hello packet from somebody else, and he's never formed an adjacency with that person, he'll then send him an update with his information. And then he'll also send a hello packet to announce himself. Now, then they'll explain, or the way the topology table works, they'll exchange other information. Hey, I'm using split horizon. Hey, thanks for the information. So I'll acknowledge that. So they'll acknowledge the updates, and then they'll tell each other other information such as, hey, here's my autonomous system number, here's my hello timer, here's my dead timer, I'm sorry, my hold timer. And then, am I using split horizon? Remember we talked about split horizon. Split horizon says, if I received an update in interface serial 000 about a network, I won't send updates about that network out that same interface. Because if I received updates from that interface, then they know more about that than I do, but I'll send it out my other interfaces. Does that make sense? Hopefully you're good with that. Again, if you forgot how split horizon or split horizon with poison reverse works, ask in class, and I'll more than show you on the board, and it'll make more sense in like 3 minutes. And then you'll be like, oh yeah, now I remember that. Don't go into the exam not knowing that stuff. Alright, so once all the routers have exchanged their updates so they're both like on the same sheet of music, then we have what they call convergence. So all my routers are converged. Once we're converged, we will only send hello packets back and forth just to let the other one know that I'm still alive. And remember, hello packets are very tiny, so they don't take up a whole lot of bandwidth. So just, hey, hello, I'm still here. Hey, hello, I'm still here. That kind of stuff. So I don't get a whole lot of extra traffic on my network. Alright, so how is that EIGRP metric calculated? You know, with OSPF we use the cost. and with RIP we use the hop count. But with EIGRP, they actually only take bandwidth and delay. That's what's used by default. So, and here's where it gets kind of weird. With EIGRP, and you will not have to ever calculate this route, at least and I've never seen anywhere where they ask you to calculate this route. They do ask you which values are turned on by default. So there are 5 values, and they are K1, K2, K3, K4, K5. So those are the weights, and we can weight different things. We can weight the bandwidth, the load, the delay, the reliability on both ends, the send and the receive reliability. So that's why there's 2 for reliability, I believe. And by default, we only put a value on K1 and K3. So remember down here, so on K1 on bandwidth, we put a 1, and on K3, there's a 1. The other ones aren't used, so they put a 0 by default. So the default formula is K1 times the bandwidth, so 1 times the bandwidth, plus 1 times the delay. Now remember, if I do a show interface, I'll see all these numbers. What's the bandwidth? What's the delay? What's the reliability? What's the load? And then you can kind of figure out what the metric would be. So it's just bandwidth plus delay. So if I jump over here, I see, here's a show interface. The bandwidth is 1555, and the delay is 20,000 seconds. So in this case, I would take 1544 and add it to 20000, and that would be my default metric. Now, again, you can modify this. The actual formula is K1 times the bandwidth plus K2 times the bandwidth divided by 256 minus the load plus K3. I have no idea what the up caret thing means. Delay, or maybe that's an asterisk. So it's times delay times K5 divided by the. So it's a big, long, crazy formula. But because by default the K2, 4, and 5 are not used, this is the actual formula. It's just 1 times the bandwidth, 1 times the delay. You add those 2 numbers up and you get your metric. So again, to my knowledge, you will not have to calculate that formula, but you will be expected to know that K1 and K3 are turned on by default with the value of a 1. And then the K2, 4, and 5 are turned off with a value of 0. And so that you know, EIGRP by default just takes bandwidth and delay into consideration. Alright, so again, bandwidth, the speed of the interface in kilobits per second. The delay of the interface in microseconds. Some interfaces are faster than others. Reliability, the reliability of the interface. How often is that interface coming up and going down? And then the transmit load and the receive load. By default it's not included, but how much load is on that network? So as far as reliability goes, the higher the number the better. 255 out of 255 is an awesome reliability. Where for load, you want smaller numbers. So a load of 1 out of 255 and 1 out of 255 is very little load, almost no load at all. So that's what you'd want to see when you look at that stuff. So remember, show interface, whatever interface you're looking for, will show you the bandwidth, the delay, the reliability, and then your 2 loads. But your numbers get bigger. Remember, if I'm trying to calculate a route from R1 to R2 to R3 to R4, I got to take every link in the chain and add that all together. So that's when you see these 20,000 delay seconds add over and over and over, and you start getting into the 100,000s, the 200. I've even seen like a million numbers pop up as far as the metric. So the further, obviously, the network is, the bigger your EIGRP metric is going to be. But again, you do not have to calculate that metric. You only have to remember it's bandwidth and delay. It's K1 and K3. Alright, you can also set the bandwidth manually if for some reason you wanted to change the calculation of the metric. Now remember, when I change the bandwidth number here, so if I go to interface 0000 and I put in bandwidth 64, that does not limit my bandwidth. It will still use all 1544 kilobits per second. But when I do a show interface, it'll only show bandwidth 64, and it'll only use 64 in the calculations of the metric. So that's all it changes, is the calculation of the metric. It does not change the actual bandwidth. The only way to change the actual bandwidth is to change cable types or increase the bandwidth that way. But it works as a system to make one route preferred over another route. Let's say I've got, I don't know, let's say I'm doing dual connections to a satellite office, and I've got a backup link, and I want the backup link to be the backup link, and I don't want to use them, but I don't want to load balance for some reason across both of them. You know, I would set one with a higher bandwidth and one with a lower bandwidth in my router, which wouldn't really change the bandwidths. It would just change the calculations so that one is preferred over the other. All right, the delays are typically standard based on the speed of the line. So Ethernet has a delay of 1,000, fast Ethernet is 100, gigabit is 10, and then we get into all other stuff. T1's 20,000, dial-up 56K, all the other stuff is all the delay is 20,000. All right, again, calculating the metric, bandwidth plus delay times 256 will give you your normal metric. So that's why you see these bigger numbers in there. So if anybody asks, or a test question asks you, you know, what is used to calculate the metric for EIGRP, you would say bandwidth and delay. All right, so dual is the diffusing update algorithm, and the idea behind dual is to eliminate routing loops and to allow faster convergence if something goes down by also not only calculating a primary route to the destination, but looking if there's an alternative route and then listing that in the topology table. So that what happens is, if a network goes down, and let's say a router goes down, your router doesn't even have to go and talk to anybody. He just says, oh, let me go to my topology table. Hey, I got a backup path right here. Boom, right back in business in less than a second. So this stuff happens crazy fast. So you don't even know that a router went down. You're like, woohoo, it's still working. That kind of stuff. So that's the big advantage to EIGRP using dual is, you know, we get loop-free networks because, you know, it eliminates the routing loops, and it creates it pre-configures the backup links so that if something goes down, it doesn't have to go and ask questions. Remember, in OSPF, they have a complete topology table in there where they have the entire network listed there. So they have that stuff. But with EIGRP, it just keeps the backup paths right there. So it doesn't really have to calculate the backup route. It already did that when it first converged. Where OSPF would have to go back to his table, and he'd have to re-examine that table to find a backup path. So as far as my understanding is, in EIGRP, if a router goes down, EIGRP will get around that faster than OSPF. Now, how fast is faster? I don't know. Could you actually see it with the naked eye? Probably not. But you get the idea. All right, now here's where it gets weird. Let's just the successor is your primary route. So that's what Cisco calls it. So if you go to the topology table, and you see there's one successor. The successor is the best path to the destination. And the successor has a feasible distance, which is the lowest calculated metric to reach that destination. So every successor has a feasible distance. But when I share that information to other routers, I report it to other routers as my feasible distance. So they don't list it as my feasible distance. They record it as the reported distance because they're getting that from another source, if that makes sense. So that's where it really gets confusing, and that's where my other video is going to come into play here. So as far as this video goes, I just want you to make sure that you understand that a successor is the primary route, and a feasible successor is a backup route. A successor has a feasible distance, and that feasible distance is then, I report my best path to other routers, and then other routers see that as my reported distance. So for me, it's my feasible distance, but for other routers, they see it as a reported distance from me. So a successor is the primary with a feasible distance, and a feasible successor is a backup route. So I know it's very confusing. So again, the other video, make sure you watch that. So remember, feasible successor is a loop-free backup path. The feasibility condition says that in order for a neighbor's route to be reported as a feasible successor, his reported distance has to be less than my router's feasible distance to the same network. And again, the next video is going to describe all that stuff. So I'm going to kind of cover this loosely and then you're going to need to watch the other video. If anybody's watching this that is not part of the class, if you go to my other videos, you'll see there's one that says something about feasible successor, feasible distance, whatever, explained. And that's like a 20-minute video where we cover all this, and it all makes a lot more sense. But I didn't want this video to be 5 hours long. Alright, so all this information is stored in the topology table. So if I go to the topology table and look here, like I'll take this one here, it shows, hey, I've got one successor, which is the primary route. So this is my successor route, and then the second route is a feasible successor. So most routes, like in the topology table, they'll just say one successor and then boom, and it's the one successor shown, because there's no backup route to this path, because it's obviously directly connected. But these other paths to 192.168.10 and 192.168.1, I do have a backup route. So I have a feasible successor. Now, again, here's where it gets weird, and here's where this is all explained in my other video. On the successor route, his very first number here is the feasible distance. So this is his feasible distance from his point of view. So in order to be a feasible successor, your reported distance, this number here, has to be smaller than my feasible distance. So all the distances from the other routers are then reported to you, and then you will list them and say, hey, anyone that has a number lower than mine will become a backup route. So here, 217.0.112 is smaller than 301, blah. So this is a backup route. Now, in this case here, now it's 301.2069. That's actually bigger than this. So this route would not be a feasible successor. This would not be a backup route because his reported distance is too big. Again, if any of that gets confusing, just skip over this part and watch the video. Or, I'm sorry, the other video. Alright. So again, there's this big, long, hey, here's how things work, I lost connectivity. Is there a feasible successor? Cisco calls this the finite state machine. It's just their logic that this is what happens when a new route's needed or when a route goes down or something. So is there a feasible successor in the topology table? Yes. Then I promote that to the successor. And then I install the successor in the topology route, and then I have selected a new successor, and I'm all good. But if not, then I need to place the network in an active state. So if I look and it says active, I'm actively looking for something else. And I'll query neighbors for a new route. And then I'll see, do I get any new routes from my other neighbors? And if the answer is no, then I remove it from the routing table, and that I can't get to that network anymore. So you get the idea. All right, so again, here... again, couldn't find a feasible successor, so I'm removing the destination from my routing table. In this slide, you can see they're entering the active state. So if I did a show interface, or if I got debugging on, remember you have to debug the EIGRP finite state machine to see all the decisions that are being made. It would say, hey, I'm entering active state, which means I'm querying other neighbors for a backup route because I don't have a path to some network that got dropped. And then, hey, I couldn't find one, so now I'm removing this destination. All right, so again, don't focus too much on the finite state machine. At that point, we're talking about network guys with years of experience that are actually digging into the finite state machine and troubleshooting with that. Most of the time, for you guys, as far as the CCNA goes, you need to focus on just getting EIGRP to work. To make sure my autonomous system number, my hello, and my hold timers all match. So, EIGRP with IP6, very identical to IP4. Obviously, I still have the neighbor table, the topology table, the routing table, and they are separate. So there's a separate table for IP4 and then a separate table for IP6. So it does not mix that stuff up. So remember, if you want to see the routing table, show IP route. If you want to see the routing table for IPv6, it show IPv6 route. All right. So when you compare the two, IP4 to IP6, in IP4 we only advertise the networks. In IPv6 we only advertise the prefix. They're both distance vectors, they both use dual, they both use bandwidth and delay, they both use RTP, so all that stuff is pretty much the same. But with IP4 you have your option of plain text or MD5, and IP6 you only have MD5 because there is no plain text, because we know plain text is not really working. You also know that the multicast address is different. In IP4, it's 224.0.0.10. In IP6, it's FF02:10. For some reason, yeah, which is A. That's really weird that they listed that as 10 there. That's odd. But you get the idea. So remember, when we assign IP6 addresses, we also assign link local addresses. So you'll see these FE80s pop up all the time in your addresses. So then here's the network we can use. So here's the IP6 addresses they're going to be using in this example. So when you're looking at the commands, you can come back here to this chart and look and say, oh, hey, here's what they're talking about. All right, wow, is that the same slide again? Ooh, went the wrong way, got all excited. All right, so same way we do it for OSPF. Instead of network statements, we actually go to the interfaces and we just turn on, we advertise them there. So in this case, we're going to configure link local addresses. So we go into the interface and we say, IPv6 address FE80:1 ? And then that says, hey, use this link local address. So IPv6 address FE80:1, and we space link local, because obviously with this question mark, they should have used link local there. So and then that creates the link local interface. So in this case, they're going to create all three of their interfaces on FE80:1. So all three interfaces are going to have the same IP6 address. Again, you can do that. Now, remember, in order to do IPv6, we got to turn on IPv6. So IPv6 space unicast routing, and then router IPv6 space router space EIGRP2, or whatever EIGRP autonomous system number you're using. Then if you want to set the router ID, you can, and then you want to obviously do no shutdown to bring whatever. That's really odd. Oh, I'm sorry. Apparently the router ID command and no shutdown in IP6 are required to form the adjacencies. Very interesting. I did not know that. So make sure you do the no shutdown on that command. All right, and then you go to the specific interfaces, and I go to the interface and just turn on IPv6 EIGRP2, IPv6 EIGRP2, and that kind of stuff. And that way, it's a lot easier to configure a router that's in two different autonomous system numbers. So let's say I've got a big network with two buildings, and I want one building to be an EIGRP2 and one building to be on EIGRP1. Well, then the border between them, that interface on both ends can be EIGRP1, and then the interfaces on the other sides can be interface, EIGRP1 and EIGRP2. So it's a lot easier to be in two different networks, I think, as far as the configuration goes in IPv6. But so again, you get the idea. So instead of doing areas, we just go to each interface and do IPv6 EIGRP2. This video is already way too long. I'm already slurring a lot of words. I'm going to go to bed. Luckily for you guys, it's just about over. All right, again, show IPv6 neighbors, or EIGRP neighbors will show me my neighbors. Hey, I got a link local at 3 and a link local at FE80:2. What interface, how long until I declare them down until I receive a hello packet. Now remember, this updates every 5 seconds, so every time I receive a new hello packet, this goes back up to 15. Then it slowly goes down, and if I don't get a hello packet until